Hello and welcome back to ECMath. This is day 2 of our 2.6 notes. You should definitely have watched the first video. This video is going to be leaping right into the midst of some really tricky rational function stuff. So I would recommend going and both watching the first video and trying all the classwork and just making sure you're a master of all of that stuff before you watch this one. That said, here we are. Let's get right into it. Hopefully this first little thing shouldn't be too bad. It's just a notation piece. We're going to look at limit notation. This is a fancy way of talking about end behavior and also just general behavior around asymptotes and holes and places where you can't just plug in a value for a function. So this is the graph and equation that we had in the last video. And it's back just because it has all the behavior we need it to have. So we're not really, we're just going to look at this graph and use it to talk about our notation. So one thing we might talk about with a graph like this is the end behavior. That is what happens over here and over here, off to the ends of the graph. And we can see that, like, if this graph were to extend, we would say that, you know, as x approached infinity, y would approach -1. It's getting closer and closer to -1. Now, we've never actually had end behavior like this before. We've only had end behavior that is infinity or negative infinity. But rational functions are different. They can have end behavior that has the horizontal asymptote. So it can be 0, it can be -1, it can be all kinds of things. Now, this notation is fine, but it's not very formal. And, you know, in Precalculus, we're working up to using formal notation. So let's add a layer of notation. So instead of writing this, as x approaches infinity, y approaches -1, we're going to write this. So how do you say this? And by the way, this is on the right because it's the right end. This guy's on the left because it's the left end. So don't get messed up by that, that we're doing this one first. So how do you say this? Well, let's take a look at what this says. First, that little lim is read as the limit. That's the first thing we read. Then the next thing we read is right down here. We say, as x approaches whatever value it is, and in this case it's infinity. Then we say, what is the function? We say of f of x. And then finally we say is, you know, whatever it is. And in this case, it's whatever the y value is. We'll say it's is y. So as x approaches infinity, y approaches -1. So we would say the limit as x approaches infinity of f of x equals -1. So there's really not a big difference between this notation and this notation, except, you know, one is more formal, and it's what you're going to see next year in calculus. So we're going to sneak it in here. We're going to start using it just to kind of get you some practice with it. So we already said this is read as the limit as x approaches infinity of f of x is -1. Let's look at this other one over here on this side. So as we extend this graph, it also would approach -1. So here we read the graph from the middle out in the direction of the arrow. That's different than when we read like increasing and decreasing. We're reading in the direction of the arrow, so we would read this as, I'm not going to write it, I'll just say it, the limit as x approaches -infinity of f of x equals, and then we say what the y is. So in this case, it's -1 as well. That's the end behavior. Actually, I am going to write this one down. So this one will write it as a sentence. The limit as x approaches -infinity of f of x is -1. Just to get some practice reading that out. Get rid of that. Okay. So that's how we read limits. It's just the same as our end behavior notation for polynomials. But let's look at this vertical asymptote. So we're going to look at this vertical asymptote at x equals 1. And what I notice is kind of a problem. There's two limits. What the heck? Because if we approach from the right, that's the left. If we approach from the left, f of x is going up to infinity. But if we approach from the right, f of x is going down to negative infinity. So how can we say that there's a single limit? Well, we don't. Instead, we use this little notation right here. We say the limit of f of x as x approaches 1 with a minus up there. And that is a superscript, but not an exponent. Superscript is high up above, but not an exponent. And that little negative means, I'm trying to get a highlighter, come on, means coming from the left, aka the negative side. So let's look at this graph, and we're approaching approaching 1, which is here, from the left. And as we approach 1 from the left, we see the graph is going up to infinity, so we say the limit as x approaches 1 from the left is infinity. But now we see this, the limit as x approaches 1 with a plus. Well, what do you think the plus means? That's right, it means from the right, aka the positive side. So as we approach 1 from the right, what is the graph doing as we approach 1 from the right? It's going to negative infinity. So we say the limit as x approaches 1 from the right is negative infinity. Let's try that again with the whole. So again, we use this limit notation for things like wholes also because we can't just write, f of 3. F of 3 is undefined. But we might want to talk about what's going on at 3. And so to do that, we use limits. We say, okay, the limit as x approaches 3 from the left, we'll say from the left, that's that minus, equals, and then we say, okay, well, as we approach 3 from the left, what does y equal? Well, it sure looks like y is approaching, even though we can't actually equal the whole, negative 3. So we say negative 3 here. Again, this is where we put the y value. This is where we put down here the x value. And this one, we see the limit as x approaches 3 from the right. We'll say from, as x approaches 3 from the right, that's thinking about this. It's also going to equal negative 3. So in this case, the left and right hand limits agreed. They were equal. But in the asymptote case, the left and right hand limits did not agree. So generally, left and right hand limits don't have to match. When you're looking at a whole, they will match. When you're looking at a vertical asymptote, they may or may not match. It depends on the function you're looking at. So here is all of that on one screen. It's just a type of notation you're going to use. You got to be able to read it. You got to be able to write it to be able to understand and talk about all the questions. It's part of our common language of rational functions. All right, moving on. Theme 2 of today is just adding some complication to our rational function graphs. So here's a function where you might just want to pause the video and try this out on your own and then see how wrong you are. I mean, you might get it right, who knows? But let's try this out together, assuming that you have paused the video maybe and given this a shot. Here we go all together. So one thing that can make these rational function graphs a lot more complicated is the need to do some factoring. So we'll just try to factor out the numerator and denominator. So that's going to be a 2x. And x squared minus 2x has a common x. So actually, let's go ahead and factor out a 10x. And then it looks like we could maybe get an x minus 2 for the numerator. Now this denominator looks a little gross. I think we should try some factoring by grouping. So we could pull an x squared out of here and get an x minus 1. And then we could pull out a negative 1 and get an x minus 1 here. So then this could be x squared minus 1, x minus 1. And then x squared minus 1 could factor further into x plus 1, x minus 1, x minus 1. And we could write that as x minus 1 squared. But this is our kind of full factoring of this thing. I'll leave that. We might need to get rid of it when we make the graph. But that's the first complication, is just a bunch of gross factoring. Okay, let's take a look at our procedure. So I've got kind of listed out all the right, the holes, the intercepts, the asymptotes, and everything, and then the sign chart. We're definitely going to need our sign chart for this one. So, holes. Anything cancel? No. Sadly, no holes in this graph. You might be saying, Mr. Eck, why are you sad there's no holes? Well, because then the equation simplifies. This equation, nothing simplifying. It's just going to be complicated. X-intercepts, those are the zeros of the top. So what makes the top 0? X equals 0 and X equals 2. A lot of people forget that this factor is a 0 when X equals 0. So don't forget about that one. Just easy thing to mix up. So we're going to have intercepts at 0, 0 and 2, 0 if we write them as coordinate points. Let's go ahead and start putting those on the graph. 0, 0 and 2, 0. Y-intercepts. Well, we can plug some stuff in. Actually, we already have it. We already know it goes through 0, 0. We could plug in 0, and we'd just immediately see that the top becomes 0. So the y-intercept in this case is easy. It's 0, 0. We already got it. Vertical asymptotes. Here we come to the factored version again, and we look at the zeros of the denominator. And the zeros of the denominator are x equals 1 and x equals -1. And I can see that this x equals 1 occurs twice. Interesting. Doesn't change the asymptote. It is going to affect the sign chart and behavior later. But for now, we can just plot in some of those asymptotes. Horizontal asymptotes. This is where we use the two-part test. We look at the degree, and we see that this one, it's actually easiest to see the degree in the unfactored version. We've got a degree 2 over a degree 3. So when we have a bottom-heavy function, then we know the horizontal asymptote is y equals 0. So we can go ahead and put in the horizontal asymptote at y equals 0. And that's all the clues we can get from this equation, right, sort of easily. And there's a lot of graph that we don't know yet. Somehow it's supposed to cross the axis here and maybe cross the axis here. There's no crossing over here at all, so it's either going to be like this or like this, but we don't know which it is yet. And we don't actually know the direction of crossing. We don't know if it's going to do that or this. So what do? Let's make a sign chart. So what goes in the sign chart? Well, it's basically all of the zeros and all of the all of the zeros and all the vertical asymptotes. Horizontal asymptotes don't matter. So we put in -1, 0, 1, and 2. And we are going to have to test 5 different zones. 1, 2, 3, 4, 5 different zones to think about the signs of each term. I'm just going to take a second and copy the equation down. Okay, let's start making our little sign chart. So again, what we're doing in a sign chart is just working from the left to the right and thinking about in each of those 5 zones, what would the sign of each factor be if we're between those x values? So over on this left side, I'm not going to worry about the 10, that just always is positive. But we'd have an x would be negative, x minus 2 would be negative, x plus 1 and x minus 1 would all be negative. So we just have 5 negative things. 5 negatives makes a negative. When we cross over -1, the top 2 would still be negative. X plus 1 becomes positive. but the x minus 1 stay negative. So we got 4 negatives and a positive. So that's going to give us a net positive. Between 0 and 1, this negative looks like it's part of the sign chart. There, that negative is attached to the 1. Okay. Between 0 and 1, so like think about 1/2 maybe. You'd have x would now be positive, minus 2 would be negative, positive, and then negative, negative. So you'd have 3 negatives, so you'd be negative. Now, let's check this out. Flipping to the other side of 1, so like maybe at 1.5. 1.5 would be positive, but 1.5 minus 2 would be negative. Plus 1 would be positive. And then 1.5 minus 1 would be positive twice, because there's 2 terms. Now we have 4 positives and 1 negative. This is still negative. So we had a sign chart that isn't just flipping left, right, left, right. We're going minus, plus, minus, minus. And then over here after 2, it's going to be all 5 terms will be positive. So that's going to be net positive. So how does that affect our graph? Well, let's take a look. And again, we're just going to kind of use this to shade the areas where the graph needs to be. It's going to have to be in this little area. Then we flip positive. So the graph's going to have to be up here. Then negative. And there is this asymptote we're going to have to follow. But then the graph stays negative. The sign chart stays negative. We had that repeated factor. And then the graph flips positive again. Okay, so there's some real complications in how we're going to make this graph. But let's just start with the left part. That's okay. This just says we don't have any x-intercepts, so the graph better do that. Between the two asymptotes, that's also pretty clear. It's just going to squeeze through here like a little cubic. Not a cubic, but like a cubic, and do this. Now, over here, we saw that as x approaches 1 from the right side, we also need to be negative. So we're going to go down again. We kind of have this like double downwards asymptote. And then it has to cross over here and go positive. But we can't just go straight up because we also have this horizontal asymptote. So what this graph actually does, and I'll show you the picture on Desmos when we finish, is it has to come up, loop around, have a little maximum. We don't know how to find that maximum, by the way. That's a calculus thing. And then come back and approach 0, like that. So this is one of those complicated things that a polynomial or a rational graph can do when you start getting enough factors in there. Also, one thing that people get really confused by or upset by is that this graph crosses its horizontal asymptote. And yeah, that's a thing that can happen too. Those horizontal asymptotes are really about the behavior at the infinities, at the left and right ends. And as long as the graph is approaching, in this case, 0, at the left and right ends, you can cross 0 in the middle all you want. It does it right here too. Vertical asymptotes, you cannot cross. But horizontal asymptotes are more about a long-term trend. So yeah, you can have a graph that crosses those. So anyway, that was the first thing I wanted to show you today, is just a more complicated rational function. And I am going to flip over to Desmos, if I can, and show you what that looks like when you officially graph it. We'll kind of see how close we got. So there it is. So we have the asymptotes at 1 and -1, the vertical. We have our 0, 0 intercept. And then we have this turning point that happens, at there. And we can see that it kind of just flattens out and eventually does still approach 0 as you zoom out. And did I get the shape right? No, it was like a little too extreme, a little too lumpy. But without calculus, you have no way of knowing the exact shape there. So it's more about getting sort of the general trends right. So, while we've got Desmos up, I want to share with you our last big idea of the unit. Or not the unit, of this section. And that is, what happens if the degree of the top is bigger than the degree of the bottom? We've looked at things that are bottom heavy, where the degree is higher on the bottom. We've looked at things where the degrees are equal. But what happens? What happens if the degree on top is higher? And I just want to share with you 2 examples of what these functions can look like. And then we'll go through and actually graph both of these examples. So it's going to be kind of a spoiler first, like we're already going to know what the graph looks like, but then we're going to see how we could actually arrive at that. So here we go. Let's take a look at this first one. Oh my gosh. Oh, look at this thing. So it appears like what's happening is we have some zeros and some intercepts, and we have a vertical asymptote. But then instead of a horizontal asymptote, it seems like the graph shoots off to negative infinity and, I guess, positive infinity to the left and negative infinity to the right. And this is something we call either a slant asymptote or an oblique asymptote or a curvilinear asymptote. There's a lot of terms for these. And the big idea is because the degree on top is higher, then this is almost like an improper fraction. And if we look at it far enough out, it kind of does sort of just start to resemble a line with some stuff in the middle. Here's an even more scary, complicated one that we will also take a look at. Again, degree on the top is 1 more than the degree on the bottom. And when we zoom this out here, we'll actually zoom in home first. We see kind of some normal rational function stuff in the middle. Then as we zoom further and further out, we see that it's just kind of shooting off to infinity. But it's not just shooting randomly off to infinity. It's shooting off to infinity along a line. And so what we are going to want to do is find the equation of that line so we can plot it. That's an asymptote. So how the heck do we do that? Well, I wrote it down for you. So these oblique, slant, curvilinear asymptotes occur only when the degree of the top is exactly 1 more than the degree of the bottom. And when that happens, you treat it like an improper fraction and you do the division problem. The quotient that you get will be the equation of the asymptote. And then the remainder, you kind of just throw it away. So, what? Here, let me show you what's going on. So the first thing you have to do if you want to find these asymptotes is recognize that this is top heavy. So we need to multiply this out. So this is going to be negative x squared plus x minus 2 over x minus 3, or negative x squared minus x plus 2. That's a 2, trust me, over x minus 3. We need to do this division, so we can do x minus 3 into negative x squared minus x plus 2. But actually for this one, because I'm dividing by a linear factor, it's going to be faster to do that synthetic division. So I'm going to put 3 in the cage, and my coefficients negative 1, 2. Synthetic division works like this. We've been doing this before. So that's the remainder. And so let's talk about what's going on here. We did this division. We haven't actually transformed anything because we're just doing division. And we've turned this into negative x minus 4. And remember how sometimes we said that you want to write the remainder separately and other times you want to write it as plus the remainder over the divisor. Well, that's what we want to do right here. So we've just done this division and we've shown that this is equal to the original. And if we think about this as x approaches infinity, this approaches 0. That little term, the remainder term, is still divided by the x minus 3. Well, that's not going to matter when x is really large. And so this is the asymptote as x approaches infinity, or negative infinity. And that's why we can throw away the remainder. It's just, it basically shrinks down because it's divided by that x minus 3 and becomes irrelevant. And we only get this guy. So this graph, if we apply the whole strategy, the first thing we have to do is plot the line negative x minus 4. So minus 4, and we go like this. We're just going to try to sketch this graph. I know we already did it in Desmos, so we're just going to try to kind of see what we can make of this on the grid that we have, knowing it already kind of what it looks like. So we have this asymptote sloping down this way. Then, looking at the equation, we have zeros at 1 and negative 2, so let's pop those in. And then we have a vertical asymptote at 3. So let's pop that in. So these asymptotes will cross kind of down here. And what that says is that this graph has to do something like this. And if I had more space, we could say, aha, it's going to come up and do this down here between the asymptotes. Now, on problems that we intend for you to do, on a quiz or something, it'll fit on the page. This is just an example where it kind of didn't fit out. Now let's tab back over to that Desmos graph and see how close we were, just based on the asymptotes and zeros that we figured out. That was not the right one. It was this one. Let's zoom back in home, and hey, we can see we had our zeros, our little curving behavior, our vertical asymptote, and we can do negative x minus 4. There's the slant asymptote. And we can do x equals 3. There's the vertical asymptote. So we really did, just with this sketch, kind of capture all the behavior of that graph. And that's how you do slant asymptotes. Let's take a minute and look at this second one that is a little trickier. All right, so this is our equation. And it is top heavy, so the first thing we're going to do is just do the division problem. So we can't do synthetic here because that's an x squared. So we have to put this into x cubed. I'm going to add some placeholders because of those missing terms just to keep things aligned, not strictly necessary, but I like them. X squared goes into x cubed, x times, then x times that gives you an x cubed minus 3x squared minus 4x. Subtract all these terms down. Be careful with your subtraction here. Biggest place to make an error, always. 0, positive 3x squared, 5x minus 8. Okay, now x squared needs to go into 3x squared, so that's going to be plus 3. And let's do this in. So we get 3x squared minus 9. Something's weird. Nothing's weird. Minus 9x. And then negative 3 times 4 is negative 12. We're going to subtract those terms down and get 0. Minus minus 9 is 14x, and minus minus 12 is 4. X squared goes into 14x. No times. This is impossible. This is the remainder, which for the purpose of this, we're just going to throw it out. We don't even care. And all we really need is this guy up here, which is the equation of the slant asymptote. The remainder's nice. You might use it for other things and other problems, but for this purpose, you only really care about the quotient that appears up here. Okay. Let's work up the rest of the equation before we go to the graph. So we already know the equation of the asymptote, but we need to factor the top, or we need to solve the zeros of the top. So we need to solve x cubed minus 8 equals 0. We could factor, but actually it's easiest to just say x cubed equals 8. So x is the cube root of 8. The cube root of 8 is 2. There's only one 0, and it's 2. Then we need to factor the bottom. And the bottom factors into x. We got a minus 4, but a minus 3. So that's got to be x minus 4, x plus 1. So the zeros are x, the vertical asymptotes are going to be x equals 4 and x equals negative 1. So we're going to have a 0 at 2, a VA at 4 and negative 1. We have a slant asymptote of x plus 3. And again, this one's going to go a little off the page, so we'll just kind of sketch it all out. These are really hard to write, such that they always fit on the page. And then we have some action going on over here that we're going to have to solve out. So let's figure out what we know from here. Another point that, as we try to solve this puzzle, these are really tricky functions. And as we put them together, it might also be helpful to find the y-intercept. I'm going to go off the page just so it's legible. So we plug in 0. So 0 cubed minus 8 over 0 squared minus 3 times 0 minus 4. It's -8 over -4, which is 2. So 0, 2 is our intercept. So that is going to be a really nice point to have. Let's make a sign chart. Let's figure this out. So our asymptotes are -1 and 4, and our 0 is at 2. And our numerator isn't really factored, but we can think about it just as its own factor, whether that's going to come out positive or negative and contribute to the top. So to the left, we'd have a whole bunch of negative things. All right. It took a second to think about that. So to the left of -1, we have our factors. We have x cubed minus 8. Now, a negative cubed is always negative. -8 is always negative. So this is going to contribute a negative on top. And then both factors, x minus 4 and x plus 1, will be negative down here. So we got 3 negatives. This is all negative. Between -1 and 2, the factor of x plus 1 will turn negative, but everything else stays, will turn positive. Everything else stays negative. So we've got negative, negative, positive. The graph should be positive. Between 2 and 4, that's where our 0 was. That's where this term is actually going to flip positive because like 3 cubed minus 8 is now positive. So we're going to have a positive on top and then a negative positive on the bottom. And then to the right of 4, everything's going to be back to being positive because there's no negatives around. So we're going to have minus, plus, minus, plus. And while I was looking at the graph, one challenge I had was thinking, and this is the thing a lot of people think, is that, oh, I need to bend around this slant asymptote or something. But remember how we talked about it? You can cross asymptotes. Slant asymptotes are the same thing. The graph actually crosses this slant asymptote right in the middle because we're positive, negative. It doesn't turn around, it just does this. The slant asymptote's only about the end behavior. We know there's no more zeros and the graph is entirely negative on the left, so it just has to do something like that. That's the only evidence we've got, so we just follow it. And same up here, the graph is entirely positive to the right of 4. No zeros, positive. That means it better just do something like that. And we had a little bit of computer help, peeking at the graph, but even without computer help, with enough time and energy and plotting and picking points, you could graph something like this with a slant asymptote. And let's flip back over to the computer and see how close we were. Okay, that's it zoomed out. Let's zoom in so we can see we have our kind of vertical asymptotes. We have our slant asymptote, x plus 3. There it is. There's our 2 vertical asymptotes, and we can really see how this graph, fits in between all of these, but you can see it does cross that slant asymptote a little bit and hits all the other points. So that's it. That was a really tricky rational graph. That's about as hard as they get, but that's where this stuff goes. So yeah, the best thing you can do now, folks, is practice. Practice all over. They're not always this tricky. But you got to know all the different tests and you got to be able to factor. There's a lot going on. Anyway, that's it, folks. Thank you for watching. I will see you all next time. Bye-bye.